Video lecture is about Raoult's law. The law was put forwarded by F.M. Raoult and it provides a quantitative relationship between vapor pressure of solution and composition of component. This law states that the partial vapor pressure of any volatile component in a solution it is equal to the vapor pressure of pure component multiplied by the mole fraction of that component in solution. So, mathematically it is represented as P is equal to P naught X. Here the P represents the partial vapor pressure of the component in solution. P naught represents the vapor pressure of pure component and X will show the mole fraction of the component in solution. Two cases of Raoult's law. In first case, the solute and solvent both are volatile, while in the second case, the solute is non-volatile while the solvent is volatile. Before going to discuss the Raoult law, first we will know about the partial vapor pressure and the vapor pressure of pure component. So here two components are taken, component A and component B. In case of component A, we will take a liquid A. In this case, only the liquid A is present, so the vapors that are produced from this liquid, it will be due to liquid A. So the pressure exerted by this liquid or the vapor pressure of this liquid A, it is represented by P naught A. P naught A is the vapor pressure of pure component A because here the pure component is present in this closed container. In case of component B, we will take another liquid B and the vapors that are formed from B, the vapor pressure exerted by these vapor, it is represented by P naught B. So here the P naught B represent the vapor pressure of pure component B. Now we will form a solution that is formed by the mixing of component A and component B. So we will mix the component A and component B and we will have a solution. Now in this solution both A and B are present. Now it is clear that both the A and B are volatile, so the vapors are formed due to A and B both. So the vapor pressure exerted by A and B, it is equal to the sum of the vapors pressure. So PT, that is total pressure, is equal to PA plus PB. It is noted that here the P naught A, that is for pure component, P naught B, that is for pure component. But here PA and PB are used, that are the partial vapor pressure of component A and component B. From the Raoult's law, these are the partial vapor pressure of component A and B. From the Raoult's law, we know that the vapor pressure of partial vapor pressure of component A or B, it is equal to the vapor pressure of pure component multiplied by the mole fraction. So in case of PA, we will put P naught A multiplied by XA. In case of PB, we will use the P naught B multiplied by XB. So it is clear that P naught A and P naught B, these are the vapor pressure of pure component, and PA and PB, these are the partial vapor pressure of component A and component B. So we will discuss the first case, the solution of volatile solute and solvent, which mean that solute and solvent both are volatile. Consider an ideal solution of two liquids A and B. So we will produce a solution that is formed from liquid A and liquid B, or mixing of component A and component B. So here these are the two solutions. So the vapor pressures exerted by these vapor, because the vapors both are volatile, component A and component B are volatile, so both will produce vapors. So the vapor pressure exerted by these vapor it is equal to the sum of the partial vapor pressure of both components. So according to the Raoult's law, PA, that is the partial vapor pressure of the component A in solution, it is equal to the pure component vapor pressure of pure component A multiplied by the mole fraction. This is the statement of Raoult's law. Similarly, the PB, that is for solution, it is equal to P naught B, that is for pure component, multiplied by the mole fraction of that component. So here the term vapor pressure of pure component A, so P naught A and P naught B, these are for pure component. XA and XB, these are the mole fractions, and PA and PB, these are the partial vapor pressure represented over here. These are the partial vapor pressure of A and B in case of solution. So we will discuss it in case of solution. Now by applying the Dalton law of partial pressure, PT, that is total pressure, that is equal to the partial pressure of the component of solution. So PA and PB, these are the two components of a solution. So the partial pressure exerted by the PA and PB, that is equal to the sum of their partial pressure is equal to the total pressure of, or total vapor pressure of solution. So we can also write it over here. PA, it is equal to P naught A XA plus PB is equal to P naught B XB. So putting their values, P naught A and XA plus P naught B multiplied by XB. These are from the statement of Raoult's law. So we will get a formula. PT is equal to, total pressure is equal to P naught A XA plus P naught B XB. And we know that the sum of the mole fraction of all the component in a solution, it is equal to 1. So here are two components present, XA and XB. So we will take a sum, and that is equal to 1. So shifting the XB to the other side, XA is equal to 1 minus mole fraction of component B. Now putting the value of XA into this equation, PT is equal to P naught A 1 minus XB plus P naught B XB. So here we will multiply it with 1 and we will multiply it with XB. So P naught A minus P naught A XB plus P naught B XB. Now we will start the equation from the positive side. So we will shift it to the start of the equation, and the other term will be moving towards the inner side of the equation. So P naught B XB minus P naught A XB plus P naught A. So XB and XB are common, so we will take it common. P naught B minus P naught A multiplied by XB, that is taken as common, plus P naught A. So this is the formula from which we can calculate the partial pressure for component A, B, or total pressure of component A and B. So first we will plot a graph. We will label it. So we will start it from X is equal to 1 and XA is equal to 1 and XB is equal to 0. So this is the extreme side at which all the components that are present in a mixture, it is only composed of A and there is no component B present. Now we will mixing it. So we will decreasing the amount of A and increasing the amount of B. So XA will become 0.8 and XA will become 0.8 and XB will become 0.2. Their sum is equal to 1. So in all cases the sum of the component will be equal to 1. So 0.6 and 0.4 will produce 1, 0.4 and 0.6 will produce 1, and 0.2 and 0.8 will produce 1, and the extreme side XA will become 0 and XB will become 1. So here we will discuss some cases when XB is equal to 0, which means that this term will be 0. So this will be 0 and any figure that is multiplied with 0, it will produce 0. Then total pressure will be equal to the P naught A. So in this case the XB is equal to 0. So the total pressure, it is equal to the P naught A. Now we will decrease the amount of A XA and increase the amount of B, which means that we are making the solution. So these all are the component of a solution. So when the solution is produced, the P naught A, that is the for pure component, it will produce PA. So XA will decrease and XB will increase the mole fraction. So in the extreme side, the XA will be 0 and XB will be equal to 1. In case of XB, XB is taken as 0 over there because there is no mole fraction of XB. And when we go to the other side, the other extreme, the XB is equal to 1. So when the XA is equal to 0, then PT will be equal to P naught B. So here the total pressure will be equal to P naught B. We will derive this formula for P naught A also, because here we will put XA plus XB is equal to 1 and XA is equal to 1 minus XB, and we will put the value of XA in this equation. If we will find the value of XB and moving the XA to the other side of the equation, then we will put the value of XB that is equal to 1 minus XA. So here we will get the XP naught B and we will get here over the XA. So when this XA will 0, all these terms will be 0 and the PT, that is total pressure, will be equal to P naught B, because in case of XA over there, this term will be P naught B. So we will get the P naught B as total pressure. So in this case here it is PB because this is for solution, and in this case it is PA taken as PA because it is for solution, while the extreme terms are for solvents only, or we can say it is for pure components only. We can also find the total vapor pressure, that is equal to P naught A and P naught B. So we will take this sum PA plus PB, we will take the sum of it and we will get the total pressure. So at any other concentration, both A and B are present. So PT is equal to PA plus PB. So in all these cases, both A and B are present. So in this case, the PT will be equal to PA plus PB because here the solution is produced. While at the extreme position, either XA will be present or XB will be present. That is for pure component A and pure component B. Second case is non-volatile and non-electrolyte solute in volatile solvent. So we will make a solution in which the solvent is volatile while the solute is non-volatile. As shown in this diagram, the vapors are produced from solvent only and there is no vapor contribution from solute. So from the Raoult's law, the vapor pressure P is given by P naught A XA plus P naught B XB. Here this term will be 0 because there is no vapors produced from the solute. So we will get P is equal to P naught multiplied by XA. XA is less than unity, so P must always be less than P naught. So it is clear from it. If we take the P naught as 1 atmosphere and the XA is taken as 0.7 because there is the contribution of XB in mole fraction also. So we will take 0.7 multiplied by 1, so we will get 0.7. So P is 0.7 while P naught is 1, which means that XA is less than unity, P is always less than P naught. From this we can say that the solute in solvent tend to lower the vapor pressure of pure solvent. And if the solute is non-volatile, so it does not contribute to the total vapor pressure, which is due to the solvent only, and it is always less than P naught. So the vapors are formed from solvent only. There is no contribution of vapors from solute. So in this case, the solution vapor pressure is less than pure component or solvent.